Welcome back, design junkies, to Mechanical Engineering Made Simple. Today we are doing a deep dive into the foundational principles that engineers use to understand, predict, and ultimately control dynamic systems.
Right. It's really a classic three-part journey for anyone building complex machinery.
Yeah.
First, you have to create a model. Then, you design the control logic. And third, and this is key, you have to make sure your measurements are accurate enough to validate the whole process.
So our mission today is to really pull out the key insights from these sources that make that whole cycle work.
Exactly.
And it all starts with modeling. I mean, why do we spend so much time creating these mathematical representations of reality?
Well, the answer is pretty simple, actually. Models are the ultimate engineering shortcut.
A shortcut how?
They're cheaper, for one,
Yeah.
and infinitely faster to build than a physical system. You can test things. Failure modes, component swaps, things that would be way too dangerous or just plain impossible to try on real hardware.
So lets you ask those what-if questions.
Precisely. For systems that might only exist on paper.
Okay, but that brings up this fundamental paradox in engineering, doesn't it? We assume the best model is the most accurate one, the one that captures every tiny detail.
And that sounds like good science, but it could be really poor engineering.
Right.
It's the trade-off. The key insight here is that the best engineering model isn't the most accurate one. It's the simplest one that still gives you the information you need.
Because if it's too complex...
If it's so complex you can't solve the equations analytically, then you're stuck running experiments on a computer simulation anyway.
So simplicity is king. You want the lowest order, most linear model you can get away with. Which I guess brings us to lumped parameter modeling.
Yes, and that phrase is so important. The real world is full of distributed parameters. Think of a long steel beam where mass and stiffness are spread out everywhere.
Infinitely.
A lumped parameter model just says, let's pretend all that mass is in one spot and all that stiffness is in another. We replace the continuous world with a set of discrete, idealized springs, masses, and dampers.
Which makes the math possible.
And the really beautiful thing is that this approach is universal. Whether you're designing a robot, a fluid circuit, an electrical filter, you're using the same basic alphabet of elements.
And that alphabet is built around energy. You have these idealized two-terminal elements, and they're defined by two variables.
Right. First is the through variable. That's the quantity that flows or gets transmitted through the element.
Yeah.
So like force in a spring or current in a wire.
And the other one is the across variable.
Exactly. That's what you measure across the element's terminals. So the velocity difference across a damper or a voltage difference or a pressure drop.
And with just those two variables, you can classify every passive element based on how it handles energy.
We put them into three groups. It's all about storage or dissipation.
So let's start with storage.
Okay, so we have the T-type or inductive storage elements. These store energy because of the through variable. The classic electrical example is an inductor, which stores energy based on current.
And in the mechanical world?
That's a spring, a translational or rotational spring.
Hang on, I thought springs stored potential energy based on displacement, which feels like a state across its ends. Why is it a T-type?
That's a great question. It's because displacement is the integral of velocity, the across variable. If you look at the fundamental math of the element, the energy storage really depends on the accumulation of the through variable, which is force in this case.
Okay, that's a subtle distinction.
It is. But let's look at the other storage type, which is maybe a bit clearer. The A-type or capacitive storage elements.
Right, the A-type elements store energy based on the across variable.
Correct. And the perfect mechanical example is a mass or an inertia. It stores kinetic energy based on its velocity, which is an across variable. The electrical equivalent is, of course, a capacitor.
So T-type for springs and inductors, A-type for masses and capacitors. That covers storage. What's the last one?
That's the D-type. Dissipative. These are your resistors. They just get rid of energy, usually as heat. So friction, dampers, electrical resistors, they all fit here.
And with just those three T, A, and D, we can build a model for basically any dynamic system.
It's the universal alphabet.
So once we've built the model, we need a standard way to write down the math. Classically, that was the input-output form, the I/O form.
Yeah, that's what most people learned first. It's kind of the black box view. You don't care what's inside. You just want to relate a single input to a single output with one big differential equation.
And that was powerful because it led to things like the Laplace transform.
Exactly. You could turn these horrible differential equations into simple algebra, which made them much easier to solve.
But getting that one equation sounds awful.
Oh, it's brutal. Think about modeling even a simple milling machine. To get the relationship between the input torque and the final table position, you have to algebraically eliminate every single internal variable, every velocity, every internal force.
And if you change just one little damper value in your model,
You have to do the entire derivation all over again. It was incredibly tedious, and that's exactly why the state variable form took over in modern control theory.
because the I/O form just couldn't handle complex systems.
It becomes unwieldy, especially with multiple inputs and outputs, and more importantly, it hides what's actually going on with the energy inside the system.
So the state variable form makes us look inside the box. How does it work?
You define a set of state variables. They're the minimum number of variables you need to completely describe the energy state of the system at any instant. If you know them and you know the current input, you can predict the entire future of the system.
And what's the natural choice for those variables?
This is the really elegant part. The natural state variables are the through variables on your T-type elements and the across variables on your A-type elements.
Yeah, the variables that literally describe the stored energy.
Precisely. It makes
Yeah.
perfect physical sense. You need to know how much energy is in all your storage tanks to know what's going to happen next.
And this lets us write the whole system down in a really compact matrix form.
Right. We use a state vector, x of t, which depends on an input vector, u of t, and two matrices, A and B. It might look abstract, but the A matrix just describes how the energy states interact with each other, and the B matrix describes how your external inputs affect them. It scales beautifully.
Okay, so once we have that solid model, we can finally move on to actually controlling the system. What's the standard structure for a control system?
It's always a loop. You start with sensors to measure the output. That measurement goes to an error detector, which compares it to what you want it to be.
Oh.
The error then goes to the controller, the brains, which sends a command to the actuators, which physically changes the system.
Let's talk hardware for a second. The sensors today are just incredible, like optical encoders.
Oh, absolutely. I think about a modern 16-bit absolute encoder. It gives you something like 10,435 counts per radian. You're resolving the position down to a tiny, tiny fraction of a degree. Your model is useless without that kind of fidelity.
And then on the output side, you have the actuator. The classic armature-controlled DC motor is a good example. The torque is just proportional to the current you put in.
Yes, but there's a really cool piece of physics in there, the back EMF. As the motor spins, it generates its own voltage that pushes back against the voltage you're applying. It's a natural self-braking mechanism.
And if you don't account for that in your model,
Your controller will never work correctly.
okay, so you've got good sensors, powerful actuators. Now for the brains of the operation, the PID controller.
PID, the bedrock of control. Proportional, integral, and derivative.
Let's break that down. Proportional, or P, is the simple one.
Yeah, it just responds instantly. The bigger the error, the bigger the control action. It's fast, but it has one major flaw.
The offset error.
The offset error, exactly. If there's any damping in the system, P control by itself can't quite push the error all the way to zero. It gets stuck at some small steady state value.
Which is unacceptable in most cases. So that's why we need the I term, integral.
Right. It's sometimes called reset action. It basically keeps adding up the error over time. As long as there's any error, the control signal keeps growing, which eventually forces that offset to zero.
It's the essential tool for accuracy.
It is. But here's that classic trade-off again. Integral action is great for steady state, but it often hurts your transient performance. It can make the system sluggish, or even unstable if you turn the gain up too high.
Which brings us to D for derivative. This is the one that looks into the future.
Sort of, yeah. It responds to the rate of change of the error, not the error itself. It's all about providing damping. If the system is oscillating wildly, the rate of change is high, so the D term pushes back hard to calm things down.
It helps the system settle faster. So why not just use D control by itself if it's so good at damping?
Because it amplifies noise. Any real sensor has some high-frequency noise, some little jitter. The derivative operation just mathematically magnifies those rapid changes.
So you'd be sending all that jitter straight to your motor.
And you could get this jerky, destructive motion. In practice, you almost never use a pure derivative. You filter it or apply it in clever ways to get the damping without the noise amplification.
Yeah.
It's a constant juggling act.
So that brings us to the final piece. We've got the model, we've got the controller, but none of it matters if our measurements are wrong. It all starts with the foundational standards from NIST, right?
Absolutely.
Yeah.
We have to remember all accuracy traces back to just 4 independent standards. Length, from the speed of light. Time, From the cesium atom, that's 9,192,631,770
It's
periods.
incredible.
Mass from the International Prototype Kilogram. And temperature from the triple point of water. Every precise measurement is linked back to those.
And we have to get our terms right. People mix up accuracy, precision, and resolution all the time.
All the time. Accuracy is how close you are to the true traceable value. Precision is just how repeatable your measurements are. You can be very precise, but completely inaccurate.
Like a broken clock that's stuck. It's precisely at 3.15, but it's not accurate most of the day.
Good analogy. And resolution is just the smallest change your instrument can even detect.
But the real pitfall in all of this is what's called the loading problem.
Yes. This is the inescapable fact that the act of measuring something changes the thing you're trying to measure.
Give me a simple example.
Checking the air pressure in a tire. The moment you connect the gauge, you hear that little psh of air escaping. You've just lowered the pressure by the very act of trying to measure it. That's loading.
So how do engineers deal with that?
We use a concept called generalized input impedance, which we'll call ZGI. It's the ratio of an effort variable to a flow variable. And the rule is simple. When you're measuring an effort variable, like voltage or force, you want the input impedance of your measuring device to be huge, as large as possible compared to the system you're measuring.
So if I'm using a load cell to measure force in a structure, I want that load cell to be incredibly stiff.
Exactly. You want its stiffness to be way, way higher than the stiffness of the thing you're pushing on. If your load cell is too soft, it deforms, it changes the system's dynamics, and your reading is wrong.
This all comes together in error analysis. Let's take that classic pendulum experiment for measuring gravity, G. The equation is G equals 4 pi squared L divided by T squared.
Right. And if you run the numbers on the most probable error, you find something amazing.
What is it?
The error in measuring the period, T, contributes 4 times as much to the final error in G as the error in measuring the length L.
4 times. Wow. That's a huge insight.
It completely changes how you do the experiment.
Hmm.
It means you can be a little casual with your measuring tape for the length, but you have to be absolutely meticulous about timing the period. Maybe time 100 swings to average out the error.
It tells you exactly where to focus your effort.
And your money.
But
Measurement fidelity isn't just about buying expensive gear. It's about understanding where the errors come from and how they compound.
so we've really covered the whole cycle, building simple, robust models with T, A, and D elements, designing effective PID controllers, and ensuring our measurements are actually trustworthy.
And it really shows the power of these analytical, linear tools. We spent this whole time talking about linear models because we can solve them.
But here's the final provocative thought to leave everyone with. Pretty much every real system is nonlinear.
That's right. Springs don't behave perfectly. Resistance changes with heat. All physical systems are nonlinear to some degree.
And for those,
For high-order nonlinear systems, there are rarely any general analytical solutions, so computer simulation is the only tool that works universally.
which is why we're seeing this push into advanced digital control. I'm thinking of modern robotics.
Exactly. To get that smooth, precise motion, they use things like the computed torque method. The controller's running so fast that it's actively calculating all the complex, nonlinear gravity and centrifugal forces in real time.
And just mathematically canceling them out.
It's the ultimate evolution. You use a complex nonlinear model, run it with incredibly fast computation, all so that a simple linear control system can work perfectly in a messy nonlinear world.
And you can't even begin to design those computational masterpieces without mastering the fundamentals we covered today.